So hello everyone and welcome back to this next lecture in the DC-DC converter series, and this is where we had left off in the previous lecture. So we had simulated a transformer, or rather we had simulated a converter where we had connected a DC source through a switch to the primary of a transformer, right? And the transformer is a simple 2:1 winding transformer. So we had connected a 24 volt on the primary, or rather 24 volt winding on the primary and a 12 volt winding on the secondary, right? And on the secondary, we have a load. So therefore we are connecting this load, but instead of just directly connecting our resistor load, we have inserted a buck stage. So what that buck stage is this simple buck filter kind of topology, which we had used for the buck filter. All right, so there is an inductor, there is a diode, freewheel diode, and there is a filter capacitor that produces a constant DC voltage before the output load. So this is where we had left off, and we had seen that this is the result that we had achieved. Right now, at first thought, it may not seem totally wrong because we have seen some kind of instability in the past. So there has been some amount of oscillations which have died down. So for all you know, this may not be a totally wrong result, but let's investigate further. And as before, let me go back to my browser. Before I start this lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you want something a little more comprehensive, I have full-length courses on the MOOC website Udemy. This is my very first course, which is simulating power electronic circuits using Python. And in this, I talk about the basics of using Python, how to install Python power electronics, some basic power electronics, and finally there is a case study of how to simulate a buck converter. If, however, you're interested more on the signal processing side, I have another course which is Basics of Digital Signal Processing for Power Engineers. And in this course, I talk about the signal processing aspects with respect to Python, how they can be done using Python. So there is a basic of signal processing, there is installation and setup of Python packages. Also, we get into the signal package with Python. And finally, there is a case study how to design and implement a low pass filter and a notch filter using frequency response characteristics with the signal package available with SciPy. The latest course is Simulation of Magnetics for Power Electronics using Python, and in this course I talk about how you can model magnetic components like inductors, coupled inductors, and transformers using Python power electronics. And finally, there is a case study of how to simulate a flyback converter. So the links for these courses are provided in the description of this video, so please do check it out if you're interested. So getting back to my actual lecture. Now, this simulation has been running for a while. As you can see, it's still running. Let me check out what's happening in the command line. There is no error. So let me go over and plot this output again. So let's go and check the plot. This is the output voltage. And so one look at this plot clearly shows something is wrong, right? Because you can see here that this is the first part where there was the oscillation. The oscillation appears to be dying down. This is when the switch is turned on. Now when the switch is turned off, as you can see, the secondary voltage, that is the voltage at the secondary of the transformer, has a huge amount of these kind of oscillations. Now, these oscillations could be for various reasons, and we will have to analyze it. But when you see a result like this, it usually indicates some form of simulation's instability, right? So to be able to analyze it, the best way is to actually generate greater plots. This way we can actually get more data and decipher what's happening. So this plot, we had plotted the secondary voltage, that is the voltage of the secondary winding, and we had plotted the final output voltage. All right. Now, let us go one step upstream and let's plot what's happening. So let me go over and show you what I mean. So if you check the secondary, we had plotted this voltmeter load, this is the secondary voltage, and we had compared it with the output voltage, that is the voltage across this. So this output voltage is the voltage across this capacitor, that is the voltmeter filter. Alright, so now that we have this, let's come back here. Actually, it is here. So we were measuring the voltage across the secondary of the transformer. What I would do is go one step ahead, that is one step upstream, and measure the voltages across the windings. That is, can I compare the primary voltage winding with the secondary voltage winding? So let's see what that is. So let me go and let me just close this and let me go back to the browser and let me create a new plot. I will call this winding voltages. I believe I may have created this before. And this is voltmeter winding 1. I'll call this V prime. And there is voltmeter winding 2. I'll call this V secondary. Let's save the waveforms and click on done. So now I have this third plot. So let me plot this. So as you can see, I'm probably generating a lot of data. That's why the plot takes time. And this is what happens when you simulate at a very low time step. So I'm going to stop the simulation because I think we have enough data. And let me go and click on the winding voltages. So here you can see there is something very clearly wrong. The primary voltage, or rather until the switch is, as long as the switch is turned on, things seem stable. Alright. When the switch is turned off, that's when things start going crazy. So I'll just go and zoom in this level just to confirm that things are indeed okay. So this is around 0.001. So let me plot before that. So let me go over and plot from. I'll just give it. You can't make it actually 0. I will have to change that. And I think there should be one more 0. Yeah, let me plot it. So I am plotting the winding voltages when the switch is turned on. This is before it is turned off, because when it is turned off, that's when things seem to become unstable. So let me go over and check it. Of course, I need to also do a Y zoom. So let me go over and let me repeat this again. It just doesn't matter as long as it's something very small. And here, the start can be, let's say, -10, does not have to be, but I'll just put it -10. And the maximum can be around 40. So let me plot it again. So when you want to start at 0, do not put 0, but rather put a very small value. It can even be 1 e raised to -6 or whatever, doesn't matter. So now we have a result. So this confirms our case that when the switch is turned on, everything is okay, right? So we have the primary voltage to be 24 volts because we have a DC voltage of 24 volts. And since we have a 2:1 transformer, we do have the secondary voltage to be 12 volts. So here everything seems okay. All right. So now the question arises, why do we have instability when the switch is turned off? Like for example, when this switch is turned off, things become unstable. So what is going on when the switch is turned off? Now, for that, we just have to go back and have a look at the circuit. So let's look at this source. We have connected a DC voltage through a switch to the primary of a transformer, right? Now, when the switch is turned on, we are applying a voltage to the primary. At the same time, when we come over to the secondary, so we come over to the secondary load, this voltage which is applied, which is available across the secondary, and when the switch is turned on, a voltage is applied available across the secondary. This is applied to this filter, right? And in the case of the filter, when this voltage appears here, that is, there's a positive voltage at the upper terminal, the diode is turned off and the current passes through the inductor, charges the capacitor and generates an output voltage, right? This is how it works. Now, when the switch is turned off, right, then the current through the inductor freewheels through the diode. Right? That should happen. But the problem is what happens to the transformer. When the switch is turned off, there is no energy flowing through the transformer, right? So like for example, let me go over to the voltage again. When this switch is turned off, no voltage applied across the primary, no voltage applies across the secondary. The transformer does not supply any energy to the load. So then the question arises, what happens to the energy that is stored in the magnetic field of the transformer, right? That's an important question. As you might know, energy cannot be created or destroyed. That magnetic field, that magnetic energy has to go somewhere. And the problem is there is no path for it to flow. It has no path to flow, right? Now, as you know from basic principles of physics, that is Faraday's law and Lenz's law, when the magnetic flux linked with any inductor or winding changes, an EMF is induced in the winding. That EMF is directly proportional to the rate of change of flux linkages. In this case, we are directly breaking the current, right? When the switch is turned on, a current is flowing. This current is increasing. When the switch is turned off, that current drops to zero. So there is a direct drop to zero. So the rate of change of current is very large, which means that the EMF induced in this transformer is also going to be very large. And that is what is causing this instability. This transformer has energy and doesn't know what to do with it, right? So the first step we have to do is we need to provide a path. Now, this is where we are going closer towards the flyback topology, right? This is why this topology that we talked about is not feasible. We need another topology. But before we go to the flyback topology, if we were to make this work, what would I do? I would need to provide some path, right? Some path here for the current to flow, right? That is, this magnetic field must have some kind of path to flow when this voltage, or rather when the switch is turned off. So let me just insert some columns and let me add a wire. Let me join this and join this. Now what I am going to do, this is not advisable, this is just to describe a concept, right? Because eventually we are going to the flyback topology, but just for the sake of an intermediate description of why we need an energy flowing through the transformer always, or rather we cannot just break the energy through a transformer, this is a solution that I will talk about. So what I suggest is I will add a resistor, right? Let me add a resistor. Let me call this bleeder because it's just bleeding, right? And let me connect this branch. So the branch is connected and we now have a bleeder resistor. So now the question is, what are we going to do? This resistance is merely a path for the current to flow when the switch is off. It should not be large, it should be a large resistance such that the current drawn is very little, right? We don't want it disturbing our circuit. So first and foremost, let me go over and let me go back and let me click on add circuit files. We have made a topological change, so we need to process our circuit schematics. And also at the same time, since circuit does not have any detectable errors, let us go and edit our circuit parameters. So this is where it was in voltage source. And this is the resistor bleeder. Let me make this 5000 ohms. Okay. We have connected a 24 volts. So 24 divided by 5000 is just a few milliamps, which is okay. So this should not seriously disturb the circuit. This is still not acceptable. You do not connect a resistor anywhere in the circuit like this, because that changes that decreases the efficiency of the circuit. Now at the same time, I had decreased the integration time step and data storage to be 1 nanosecond. Now this was only because we thought that the problem lay with the integration time step. So let me go and just bring this back, because I don't think that really helped. Let me go back to the main page and view output. Now before I run this simulation, I will also change the time step in the transformer model. I'll make this also 1 e raised to minus 8, right? Because our initial hypothesis was that our integration time step was too large, and that is the reason why there was instability. But we find that that probably is not the reason, because even making it 1 nanosecond did not improve the stability of the system. So let us go back and let us now run this simulation. So as always, let's go to the console, make sure there is no error, there is none, so we should be okay. So let's go try again to plot the output voltage. It may take some time, which is okay. And you see that the result is much faster, because we have, and you see this is the impact of having a smaller integration time step, right? This is how much faster your simulation runs. Now, I think I may need to run it once again. And let me do so. Right? You see now the problem seems to have gone. We are plotting again the secondary voltage and the output voltage. There is some amount of oscillation in the beginning. That's only normal. That is a simulation. That is a simulation oscillation. So for example, when you simulate a system, and especially when you simulate a system that is starting from rest, it takes some time for the variables to adjust themselves, right? So therefore, this amount of oscillation is only expected, right? But the oscillation dies down. What is important is that when the switch is turned off, the old large oscillations that we were finding are no longer there. Now you see that the secondary voltage when the switch is turned off is now at 0. And most importantly, you can now make out that the output voltage is indeed increasing, right? So the buck filter that we added is indeed causing a gradual increase in the output voltage. So the voltage that is fed to the output load is now going to be a steady output, right? So this means that our hypothesis that the transformer energy had nowhere to go and was causing the instability was correct. Once we connected a resistor, we now see that the transformer, this simulation instability is now gone away. Now let me go plot it again, and let me also plot the winding voltages. And let me plot the winding voltages. So let's check them both out. And you see, now we have a repetitive waveform, right? Now, of course, there does seem to be some amount of question as to what this is, because most importantly, you see the biggest cause of concern is that this actually oscillation is increasing. And if this keeps increasing, we might result in instability, but that's something we'll solve later. But most importantly, you see now we have a switched waveform, right? We do have a switched waveform. So there is this waveform, switch is turned on. When the switch is turned on, the secondary voltage is at 12 volts. When the switch is turned off, it is 0, and it repeats itself. And the output voltage, right, which is the output of the buck filter, is gradually increasing. So now we see that the simulation is working. Let me just check the winding voltages, and we see a similar pattern here as well, right? So you see that since it is primary and secondary, we do have a ratio, a 2:1 ratio, right? Now there are these spikes, and these spikes are still because the system still has some amount of instability, and that reason is because we have made a makeshift solution of just connecting a resistor, right? We need to conclusively solve this. But most importantly, we now seem to have some semblance of a converter going, right? Now, question is, why is this topology not still what we want, right? The reason, simply speaking, is we cannot just connect a converter resistor like this, right? We've connected a bleed resistor, And the reason for this bleeder resistor was that the magnetic energy in the transformer, and therefore the induced EMF that is produced when the switch is turned off, must have a path to flow. Alright, and this bleeder resistance is the path. But a resistance like this is not at all recommended because this decreases the efficiency of the system. Right? And that is the reason why this topology is not at all acceptable. Right? And this is where we are now moving closer to the flyback topology. Right? This justifies the need for a flyback topology, and in the next few lectures we will start talking about the flyback topology. But what is important is that we gradually built up, right, to the level of some form of a converter, and we showed the need to how, or rather we showed the necessity of managing the energy in a transformer. The most important thing is the energy in a transformer must always keep flowing. You must not break the current in a transformer, right? When you're energizing a transformer, the magnetic field builds up, the magnetizing current increases. This magnetizing current should not be broken to zero. If this magnetizing current is broken to zero, the energy in the transformer has nowhere to go. Alright, that is not at all recommended. Right? So therefore, this arises that what do we do with the energy in the transformer? And this is where the flyback topology solves this problem. The flyback topology ensures that the current in the transformer is always flowing. Right? And how does it do so? It does so by a very clever trick of managing the winding polarities. So this is something we will talk about in the next lecture, which will be next week. So with this, I will end this lecture. If you have any doubts, please do post either in the comments or email me or message me on social media, whichever is your preference. Otherwise, I will see you next week. Thank you so much and goodbye for now.